What's up, scholars? Today we are going to be working on our bridge project. You're going to be graphing parabolas, and you're going to do that using this document. So if you haven't, go ahead and make sure you've got this open, and we'll pause the Edpuzzle and let you go over and fill in your answers. You'll be turning this in for points, so please make sure you complete this document as we go along. So we're going to actually go through this document together so that you've got some additional context and some more information about bridges and parabolas. So this might be one of the most famous bridges in the world. This is the Golden Gate Bridge in San Francisco. It's called a suspension bridge because of these suspension cables. Now, I won't tell you until a moment from now, but some of these have this mathematical parabola shape to them where they're kind of curvy and go down nice and low. What do you think the bridges use parabolas for? I want you to answer this question before we move on. Why do you think bridges use parabolas? Hope you've got your answer typed into here on your document. The reason that bridges tend to use parabola shapes, and here's what we mean. This is a side view of the Golden Gate Bridge. It's shaped like a parabola because this helps to support the weight of the cars and people that cross that bridge every single day. Many thousands of people cross that bridge to go from Oakland to San Francisco or the other direction every single day. So this parabola shape can be graphed in this generic way. Y equals A times the quantity X minus B raised to the second power plus C. Now, we won't explicitly use this form, but it's kind of fun. It makes graphing parabolas a lot easier, and we've done some work so that you can see what the equations of these different bridges are across the country. Part of what we're hoping is that you will begin to understand how this equation sort of works, what each term A, B, and C will be for this. So I'll let you take a look at that, but we're going to explain as we move forward. So I won't give the details of how this works, but basically you can take three pieces of information to determine the equation for any parabola. All you need to know is its longest span. So on a bridge, a span is between these two uprights. What's the longest span? What are the height of the towers, or the height of the roadway? So these towers go 500 feet above the road's surface, and they are about 8 feet above the surface of the road down at this lowest point. So that's the three pieces of information that we've got here. So again, I'm not going to show you exactly how we did it, but we ended up with this equation. This equation describes the Golden Gate Bridge with all the detail I just gave you. So what you can do, and I'm going to encourage you to do that, is you can open up the graphing calculator on Desmos and you can plug that in. I want to try to show you that now. So what does the Golden Gate Bridge look like plotted in Desmos? Let me try to show you how that is going to work. So we'll do y equals 492, we're using this equation here. And then if you do the division symbol, it will give you a fraction. So then 441 followed by 4 zeros. So that's the A term out in front. Then you do x minus 2100. That's half of the length of the longest span, plus 8 feet above the roadway. Now you might say, okay, I've plugged that in. Where is my graph? The graph is here. If you zoom way out, you can see the Golden Gate Bridge. So it has that very familiar looking shape to the Golden Gate Bridge, just like we saw here. The only difference is on this one, I've put some points on there to highlight a couple of things. So for example, now I'm just going to look at what's on this document. For example, we've got what's called the vertex. That's either going to be the lowest point for bridges that open like this, or it's going to be the highest point for future bridges, which we'll look at. You've got the leftmost point and the rightmost point. So my question for this one is, does this parabola open up like a cup or down like a frown? Go ahead and answer in slot 2. And of course, this opens up like a cup, so make sure you've got that typed into blank number 2, up like a cup. All right. Now, I want to sort of skip ahead a little bit. I'm going to ask you to answer these questions on your own. You can do the same business we just did. You can use Desmos to do it, and you can graph this local bridge. This is local to Indianapolis. It was closed for a while. They were doing some construction on it, but now it's open. It's on Central Street, or Central Ave, I suppose. We'll change that. It should be Central Avenue Bridge in Indianapolis. It's very close to Heron. This one's quite a bit smaller. Its longest span is only 76 feet instead of 4,200 feet. The roadway is about 30 feet above the water. So you can use that information to calculate the equation. And again, you can graph it. I'm going to encourage you to do that and then answer this question. You can also just look at our picture here. Does this parabola open up like a cup or down like a frown? This parabola opens down like a frown. You might start to figure out what's different between those two equations that makes this one open down, just like the shape of this bridge, versus the Golden Gate Bridge, which opened up like a cup. And that has something to do with its equation as well. Next, we're going to do, I'm going to ask you to answer what looks different about this from the Golden Gate Bridge. And of course, you can use Desmos to help you there. You can take the graph, the graph that we've got going here and plot the Central Street Bridge against it. And you can use it to help you compare. Quite a few things are different between this and this. Just look at the points that are plotted. Okay, so you're answering number 4. Okay, one of the things I noticed is that the Golden Gate Bridge much smaller than the Central Street Bridge. It also opens the other direction. The Central Avenue Bridge opens down, down like a frown. The Golden Gate Bridge opens up like a cup. Okay, continue. Okay, on to the 30th Street Bridge here in Indianapolis. Some similar information. You can represent the 30th Street Bridge with this equation that I'm highlighting down here by just knowing the length of its longest span, which is here in the middle, 116 feet, and the height above the water, about 35 feet. So when you graph that, again, you can use Desmos to do so. You end up with the Central Ave Bridge and the 30th Street Bridge plotted next to each other. And again, answer the question for the 30th Street Bridge. Does it open up like a cup or down like a frown? And then I want you to, in a moment, answer on your own. What do you notice about how this graph looks different from the graph for the Golden Gate Bridge versus the Central Ave and 30th Street Bridge? So compare these two to the Golden Gate Bridge. Go ahead and do that now. So I noticed, compared to one another, the 30th Street Bridge, its vertex, the highest point, is a little bit higher than the Central Avenue Bridge. And it is also a wider span, a wider bridge. Its size is bigger. Compared to that, I'm going to flash up. I've got all three plotted together. Compared to the Golden Gate Bridge, which is the red one here, they are quite small. And again, they open in different directions. So make sure you've got something like that here in this blank. So for our last little bit here, we're going to try to have you figure out in this equation, what does what? What does A do, what does B do, and what does C do? To help you with that, I'm going to give you a couple other bridges. You've got the 16th Street Bridge in Washington, D.C., which looks like this. It's a fairly iconic bridge in Washington, D.C. And you're going to compare that to the Verrazano Narrows Bridge in New York City. This is a view from Brooklyn at the Verrazano Bridge in New York City. So we're going to compare those two directly, and that will help us with the comparison. So again, what I want you to do is to have Desmos open. I want you to do this on your end of things. And I'd like you to plot these together. Again, I want to just quickly show you one, and then I'll pause and show the rest. So this will be the 16th Street Bridge. So this one will be y equals negative, that's important, 45, and then I'm putting the divide button to give me a fraction bar, divided by 62.5, all of that is squared, oops. And then we're going to multiply that by the quantity x minus 62.5, all squared, plus 45. So that, let me make that bigger, that is the 16th Street Bridge in Washington, D.C. I'm going to pause and do the same with the Verrazano Narrows Bridge in New York City. So here they are, again, plotted together. And what I'd like to show you is the structure of this equation. We'll go back for just a moment here. Oop, there it is. So you've got to plot a parabola, y equals a times the quantity x minus b raised to the second power plus c. I want to show you what that looks like for these equations. So this is the a term. It's everything out in front, including the negative sign. That's our a term. X minus b is this term here, plus c is this term here. You'll notice for the Verrazzano bridge, it's a out front, b, and c. So what I want you to put in here, what do you notice about the two bridges? What is the same? What is different? And then you're going to do the same activity for the Golden Gate Bridge, the Central Ave Bridge, and the 30th Street Bridge as well down here at the bottom. When you do that, I want you to answer what's different and the same about those three bridges. And then finally, what I want you to do is answer these questions A, B, and C. This is, again, you're going to be turning this in on Google Classroom. Along with finishing watching this Edpuzzle, you'll earn credit for both of those activities. Scholars, thanks so much for learning with me about bridges and parabolas. I'm hoping now as you move throughout the world, you'll see more parabolas, including on bridges, just like these. Thank you so much, scholars.